Hello, and welcome back to Math 146 video recordings by Chad Bemis. Today we're going to talk about Module 2.1, Scatterplots and Correlation. Remember that from OLI, this is the case quantitative to quantitative when we create a scatter plot. The scatter plot is a set of ordered pairs plotted on the x and y axis that give us information about the variables that we're talking about or the data sets that we're talking about. So we want to be able to determine relationships by looking at a picture of the data, as we've talked about before. In the case of quantitative versus quantitative, it's very nice to plot them as ordered pairs. In other words, points on the axis. And this enables us to see the relationship, if there is any. So whenever there is a cause and effect relationship between the two variables, we say they are related or correlated. And this is when one variable or set of data causes or influences the behavior of another variable, and the variables are related. So for example, calories consumed, we call this the explanatory variable, versus weight gain, the response variable. Now, correlation in itself does not imply that one of the variables or data sets influences or changes the values of the other data set. It could mean that they're related, but one doesn't cause the other. So in the example of the hormone replacement therapy for women, it was at first thought to cause either the improvement in the coronary heart disease. In other words, women who got the hormone replacement, it was thought that it helped their chances of preventing coronary heart disease. Well, as it turned out, that was not the case. What happened was that the women who had a lesser chance or a lesser incidence of coronary heart disease, who were getting hormone replacement therapy, there were other looking variables involved, such as socioeconomic status. The women that were getting the HRT were richer. They had more money. And so women or people who have more money tend to have better health care and are healthier. So it does not always imply, one does not always imply the other if they're related. Okay, there's lots of other examples as well. So when we say positive relationships, remember we're thinking graphically. So graphically, if we have ordered pairs that do this, we're talking about a positive linear correlation because the slope is positive. Remember that slope is rise over run. So if we have a positive y change and a positive x change, we end up with a line that goes upwards from left to right. That's a positive relationship. It doesn't necessarily have to be linear like this. It could be curved one way or the other. But as long as it goes uphill from left to right, we're talking about a positive relationship here. So as one variable increases in value, so as the x-axis increases, the second variable also increases. Remember, that doesn't necessarily mean causation, but a positive relationship here. Okay, negative relationship, as you can imagine, is one variable goes larger or higher, the response variable goes down. So what we get is a negative line or a negative relationship here. As one increases, the other decreases. So if the variables are a and b, as a goes up, b goes down. And if a is plotted on the x-axis and b is plotted on the y-axis, a goes up means to the right on the number line. B going down means going down on the y-axis. So we're looking at that type of relationship there. Linear relationships are what I was talking about earlier. If we plot the scatter plot and we're able to draw a line through most or many of those data points, we can say that there is a strong linear correlation or strong linear relationship, either positive or negative. Nonlinear relationships, if you plot the two variables and it just looks like stars in space, for example. Then you've got, a scatter plot here that really implies no relationship whatsoever. So if this is your first quadrant, remember that most scatter plots are plotted in the first quadrant because x and y are usually positive, right? The variables that we study are usually measures, ages, weights, heights, right? These are all positive and 0. We don't have negative heights. So in this case, there would be little or no relationship between the two variables. Okay, so as I mentioned before, the scatter plot enables us to visualize this relationship or non-relationship. Again, the rectangular coordinate plane just means the x and the y axes. And again, usually the first quadrant, which is where both x and y are positive, is where we plot these points. And we don't necessarily connect the points, although later on we're going to talk about how to plot the line of best fit, right? But rather we keep them as separate points, ordered pairs. Each ordered pair has an x coordinate here and a y coordinate that makes up where the location of the point is, as you may recall from elementary algebra. And again, we usually only use the first quadrant of the plane, positive values for x and y. So the x-axis, or horizontal axis, right? Let me clean this up a little bit. The x-axis, once again, is used for inputs, or what we usually call the explanatory variable. Okay? Predictor variable, explanatory variable. The y-axis is used for the dependent variable, outputs, also known as the response variable. Okay? So, explanatory, response here. For example, there may be a causal relationship between hours spent studying, maybe for this class, and grade on the final exam. Okay, maybe. Many times it is, but not always. So we could put number of hours studying, hours here, on the x-axis, and the grade, or GPA, on the y-axis. And if we plotted the points, there'd probably be some, above and below the line of best fit. But probably what would happen is that in general, it would have a positive relationship. So in other words, the more hours you put in, the better your GPA. So here's another example. We have 14 children who are pediatric primary care patients and their corresponding heights. So you may want to know, okay, how do I plot these on the calculator? You can certainly pull out a piece of graph paper, label the axes, but most people don't want to do that if they don't have to. Plus, if you're plotting on graph paper, there's really nothing else you can do with it other than look at it. So one of the things that we can do is we can do these instructions here on the TI calculator, and we can type these, we can follow these instructions, and then you can see how we create a scatter plot. All right, so we turn the calculator on, and then we click the Stat button, go to the Edit menu. Number 1 is Edit, and as you can see in List 1, I've already typed in most of the ages here, but I left a few so that I could show you how we type them in. It's very simple. So it looks like I'm up to the 4.2 here. So I have, looks like I have 3 more to do. So I would type in 4.5 and then hit enter. 4.8, enter. And 5.1, enter. So once I have all of those data values for age of the children in the first column, I can hit the right arrow key, and then it'll go, when it's blank, which it will be when you type it in, it'll go to this first entry. So you'll type in the 29.4, which should correlate to the 1. Notice it says 1 instead of 1.0. Right? If I typed in 1.0 for that value, it'll still just call it 1. Okay. Anyway, so in L2 or list 2, I type in all of the heights of those children. So let's go down to where I haven't typed in yet. So the 12th value is the child who is 4.5, aged 4.5, and 43.9. So 43.9, 44.5, 45 points. Is that 8? Yes, 8. Okay. So go ahead and pause the recording and go ahead and finish filling out those lists. All right, so now you've finished filling out the lists. What do we do next? Okay, so to turn on the plots, we can hit the second key. Notice it makes a little arrow. And then the y equals key says stat plot. If it's off, we hit enter and turn it on. Remember, you can pause and rewind this video at any time if I'm going too fast. Turn that on, and then this should light up plot 1. Excuse me. And then for the type, the default should be a scatter plot, which is this box here. And the mark you can choose, and you're using list 1 and list 2 for the X and Y list. You can use a square, a plus sign, or a dot. I like to use square because it shows up a little bit better. Okay, so once we've done that, and all of this is correct, we can hit the zoom key, because what we want to make sure is that all of those data squares are in the graph that we can see. So one quick way to do that would be to use zoom stat. Another way would be to use the window function and select, x min would be 0, x max would be anything larger than 5.1, right? So then all those values would be included. But the quicker way to do it would be to just go to zoom stat, which is 9. You can also hit the 9 key, right? And then you can see the scatter plot here. Let's zoom in a little bit. So what type of relationship do we have with this scatter plot? Remember, these are 14 children. The x-axis is their age, and the y-axis is their height. Okay. So again, the previous example shows a positive linear relationship between the x and the y variable. This occurs when the slope of the line is positive. Now, can you explain why the slope is positive in this case? Just reminding you the picture of it looked like that. So why is the line going up from left to right? If you guessed that the line is going up because the older the child, the taller they are, well, then you guessed right. So it should make sense that a toddler, right, will be shorter in general than a 5-year-old, right? The toddler was 29 inches tall or high, and the 5-year-old was 46 inches. That's to be expected. When the line goes down from left to right, we say it's a negative linear relationship, as I mentioned before. So here are all different types of scatter plots that you can see. If all the points line up perfectly, and you can draw a line through all of them, I didn't draw that very straight. But anyway, we call that a perfect positive linear correlation. If most of the points fit on that line, it's a strong linear correlation. You'll note that, I don't know if you can see it, it's a little small, but it says R equals 1, R equals 0.9, R equals 0.4. The little r that we're talking about here is called the linear correlation coefficient. Coefficient usually just means it's a number. So the coefficient itself will be a decimal number between -1 and 1. And the closer it is to those extreme points, the more strong the linear relationship is. So you'll note that if I have r equals 0.9, which it is right there, it is a strong positive linear correlation, or strong. Yeah, in this case it is positive because it's a positive number, right? So if I had r equals -0.86, it would also be a strong linear relationship, but it's negative, which means that the line would be going down like that. A weak positive linear correlation, there's some activity here to indicate that as the explanatory variable increases, the response variable increases, but there's a lot of fluctuation here as well. And then we can do the same thing with the negative linear correlation, strong negative linear, weak negative linear, and then here we just have points in space, as I mentioned before. There's no relationship between the two variables. So for the next examples, let's think about if there's a positive linear relationship or correlation, a negative linear correlation or relationship, or none at all. Okay? So again, you can pause in between each example, if you like, and ask yourself these questions. How about hours since last meal? So that's the response variable. And blood glucose level. This is the explanatory variable and the response variable. My bad. What do you think? So again, hours versus the glucose level. I'm thinking that as time goes by, the glucose decreases. One of the reasons why you have a fasting blood glucose level if you're trying to determine diabetes or high glucose levels. So I believe they are related, and they are related negatively. In other words, as time increases, glucose level drops because you haven't been eating. I could be wrong, by the way, but I think that's correct. Next example. Let me clear this off. Price of a used car and its odometer mileage reading. Okay. Price of a used car and its odometer mileage reading. So what this means is that when you buy an expensive car, how many miles would you expect to already be on it? When you buy a car that's a little bit cheaper, how many miles would you expect? Let's say it's the same car, right? Let's say it's a Honda SUV. So as the price in dollars goes up, what would you expect the mileage reading on the odometer to do? Go up or down? Correct me if I'm wrong, but I believe it goes down, right? Because if a car is expensive, right? If a car is expensive, usually that means that it has a low mileage because it hasn't been used as much, right? So it's in better condition. When the price is lower, you would expect the odometer reading to be much higher, right? So for example, you may have a Honda that costs $2,000, but because it has 150,000 miles on it. Or the same Honda might cost $4,400, but it only has 28,000 miles or something like that. Hopefully that makes sense. So we said that this was a negative linear relationship. We said this was also a negative linear relationship. Age of a patient and the amount spent on medication. So as patients get older, what happens? Well, I think we all know in general that the amount spent also goes up. So that would be a positive, right? Positive. Eye color, shoe size. As far as I know, there's no correlation. There's no relationship. So we would say none on that one. The number of absences and the final GPA for a math class. You should know the answer to this, but if you don't, the more you attend, or I should say the less you attend, right, the more absences you have, that tends to not necessarily cause, but be correlated to the final GPA. So we would have a negative relationship here. So the fewer absences you have, the better you'll do in general. So I hope you heed that warning. How can we measure the strength of a linear relationship? Okay, I talked about this earlier with the correlation coefficient R, which is a number between -1 and 1. Remember that when R is negative, we have a negative. R is negative. We have a negative relationship. When R is positive, we have a positive relationship. It's as simple as that. So again, R equal -1 gives you a perfect negative. And then in between -1 and 0, we have strong, moderate, weak, right? Weak, moderate, strong, positive relationship. So we're talking about numbers on the number line between -1 and 1 here. So here's an example of, well, here's the formula to calculate R. No thanks, don't want to have to do that. How about we just use the calculator to do it instead? Do you agree? I thought you would. All right, so here's how we do it. We create a list of values on the stat menu, okay? Make sure the diagnostic is on, and I'll show you how to do this. We're going to use the calculate menu on the stat and linear regression, and we hit enter twice. So I'll show you the example. R should be toward the bottom of the list or at the bottom of the list. There'll be an R squared value and an R value, so you're looking for the R value. The rounding rule is just go ahead and round it to 3 decimal places. Sorry, I went a little too fast on that one. All right, so here's our tables. All right, there's a couple of them. The first one is age versus class size. You can think about whether these should be related at all. Okay, so once again, I have these already pre-plotted on the lists 3 and 4. So you can use list 2, you can use list 3 and 4. So I've got age is 1, 2, 3, 4, 5. And I've got class size is 7, 15, 8, 14, and 6. Okay, so step 1, we go second, and then catalog, which is the 0 key. Then to get down to the D's, which is the alpha right there, we hit the X-1 or reciprocal key, because it's already defaults to the alphabet. Find the diagnostic on, hit enter, then enter one more time, and it should say done. Once that's finished, then you can go stat, over to calculate, linear regression, which is 4, or you can hit 4. You can either use the arrow keys or hit the 4 button. But now we're using the, excuse me, the list 3 and 4. So I need to go second, list 3, comma, list 4. Once again, if I'm going too fast, you can always rewind and catch back up. Enter. There's the value of R right there. -0.113. So if we're rounding to 3 decimal places, it would be right there at the 3. So you can ask yourself, is this a strong, is it negative or positive? Well, hopefully it's obvious that it's negative, right? And is it strong, moderate, or weak? It looks like a weak negative correlation. Or it might be small enough that we could say no correlation. We could say both. No relationship between the two variables. All right, next table. Age and diaper changes. Age and diaper changes. You can ask yourself once again, should these be related? All right, so we can type this data in. I'll have you type these into your calculator yourselves and see if you can come up with the correlation coefficient R. All right. So go ahead and pause the video and do that now. All right, hopefully you've got your correlation coefficient ready to go, and let's compare it with the slide. Negative 0.993 here. So it looks like it's a very, very strong or perfect, strong or practically perfect negative relationship. Sorry, I'm using a lot of abbreviations here. Negative correlation. Exclamation point. Happy face. Now this is my one-eyed or Cyclops happy face, which I call Mike Wazowski. And that's the end of the show for this time. See you on the next one.